Oh, wait.
Oh,
Wait, I hit
yeah,
broadcasting. Hold on a minute. Hold on. Oh, no.
that's okay. It's just gonna,
Oh, you can't stop it then, right?
Oh, sorry,
no.
Christina.
It's okay. It's not a big deal.
Hold on. I think you can stop participants. Oh, no.
It's okay. People are coming in, so it's okay. Let's see here. I'm gonna pause.
Through that, like, it's weird to hear my own voice come out of the screen. It kind of throws me off a little bit. Like, wait, what am I doing wrong here? So.
The last couple of years I've had my class recorded because it's an online class. That seems really weird. Not only is it your voice, but you're walking around and I don't know. It was really weird the first few times.
Are you teaching over the summer?
No.
Like...
The BASE classes that I've taught in the past couple of years have been online. We have an online master's program that's part of.
Oh, right. So, are you guys going back in the fall?
Yeah, that's the plan so far. I don't know. I'm teaching online, like it's synced, so the students come in at the same time I'm there, and I'll just go through Zoom or something. But I don't know. There's a good chance that doesn't happen, I'd say.
Yeah.
Well, that'll happen, but there's a good chance that there's no face-to-face classes at all.
Right. Right now it's mixed, so there's like small classes are face-to-face, but everything over like 50 people is online. So, but we'll see if that holds. Who knows?
Yeah. We did get a lot of pressure to make classes more face-to-face. They didn't twist anybody's arm, but they encouraged us to make it more face-to-face.
Yeah. So we'll see if see what happens over the next month, I guess.
It's tough calls. I mean, for universities everywhere, I mean, it's so much money. If you don't charge students room and board, it's tough to keep it going.
Right.
Okay. We will wait one more minute and then we will get started. I just want to make sure that everybody can see the first slide. Okay. And we have started the recording, so we are good there. All right. All right, let's get started. Hello, everyone. My name is Christina Wolford. I'm the Director of Operations for the International Biometric Society. And on behalf of the staff of the International Biometric Office, I would like to welcome you to the second week of our virtual International Biometric Conference. Before we begin, I would like to share a few housekeeping items. First, as you familiarize yourself with Zoom controls, we recommend that you choose the full screen option for the best view of the session. In particular, this allows you to easily toggle between a screen that shows the presenter's face and a screen that shows any slides being displayed. Second, as a reminder, this session is being recorded. Attendees will be muted during today's session. However, attendees will have the option to share their reactions using the chat feature and ask questions of our presenters and staff throughout the Q&A feature. We ask that all of your questions be sent through this Q&A feature. Note that this option is only available during our live IBC sessions. You can also share your reactions before and after this session through the new IBC community, which you have access to because of your IBC registration. To visit the community, go to ibc2020.org and log into your account and click on the community tab in the primary navigation. The community also offers more information on future sessions, as well as direct links to each and, in the future, recordings of all previously recorded sessions. Finally, if you experience any technical difficulties with the session or with the IBC community, please send a message to ibs@biometricsociety.org. This address is being actively monitored so that problems can be addressed quickly. Now, it's my pleasure to introduce our host and executive editor of JABES, Brian Rich.
Hey everyone, and thanks Christina. Thanks to everybody for coming. So I am the editor-in-chief of JABES. I've been editor-in-chief now for about 1.5 years. And the concept of this award, every 2 years, JABES picks a couple of papers that were the top papers published in the last 2 years to sort of showcase the great work that's taking place in our journal and encourage people hopefully to follow up with our papers and to submit their own papers to our journal. So this paper I picked because I think this is super useful for my own research, and I know it is the most highly cited paper in JABES in the last few years. Analyzing large spatial data sets has been one of the biggest problems in the field of spatial statistics and thus environmental statistics for maybe a decade. And there's been an incredible amount of research done to the point now where there's maybe 5 to 10 different methods that are all applicable when you have 1 million observations, which is something that 10 years ago, I'm not sure any of us knew was possible. So this paper is a great summary of those methods. It categorizes the methods into different groups and gives different tactics for how we might handle this really important problem. And it's also really clearly written. And so I've been using it as a reference in my spatial statistics class. I've also been referencing it in my papers. It's just the way that people should go about thinking about this problem. So I'm excited to see Matt's talk on this. Matt, the speaker, is the first author of this paper. The authorship is pretty long. I think there's something like 20 authors on this, and maybe Matt will tell you the story of how this came about when he introduces the paper. Matt is now an associate professor at BYU in the US, Brigham Young University. I first met Matt a long time ago, probably longer than either of us want to admit. Matt was a graduate student at this research program at my university. I was the mentor of a small research team, and Matt was a student on one of the other research teams. And I remember this 2-week program just struggling mightily to get my group to do something like linear regression and write a reasonable paper. And this was like the most stressful 2 weeks to get my team to do this. And then Matt, this guy who I'd never met, comes up and presents his results. And it was this amazing Bayesian hierarchical model. I think it went on to get published in either JABES or Envirometrics. So I remember leaving this thinking, I am the worst mentor ever. I need to go rethink the way that I'm doing this. But now I feel better because Matt's done great things at BYU. So I know that this was Matt being exceptionally good and not me being exceptionally bad. Okay, so Matt's going to give the talk has been pre-recorded by Matt to avoid audio problems. But Matt, maybe you want to say a few words about it before we start the recording?
Yeah, sure. So thanks so much to the organizers, and particularly thanks to Brian for inviting me to give this talk. This was a really fun paper to put together, and as you'll see, it's extremely collaborative. So I have to give most of the credit to my co-authors on the paper. I was mostly the facilitator. So because it's a pre-recorded, I'm going to be monitoring the chat. So if you have questions during the talk, feel free to put them up on the chat, and I can answer them in live time. So again, thanks for letting me come and present.
Hello, everyone. I want to thank everyone for taking the time to come out and join this webinar today. Obviously, I wish this was under better circumstances. We could actually be together, but given the circumstances, I certainly hope everyone's staying healthy and staying safe. I want to thank Brian Rich, particular, for inviting me to give this talk and present this paper that I worked on with a lot of different people. Well, I'm the first author. I have to give full credit to all of my co-authors, of which there are many, as you'll see. They're the ones that made this happen and really put in a lot of the work to make this paper come together. So I'm excited to share it with you guys, and it was a fun paper to work on, and I hope it helps you in your work as well. So the topic of the paper that we're looking at today is computing for Gaussian processes. So when you use the Gaussian process for machine learning, for analysis of spatial temporal data, or emulating computer models, whatever it is you're using Gaussian process for, the issue you run into very, very quickly is the likelihood contains both a matrix inverse and a matrix determinant. Now these matrices, because of the Gaussian process assumption, they're usually very dense. And as soon as your sample size gets large, these matrices become very difficult to work with, and computationally can be very, very slow. Just to give you an idea of how slow this can be, I just timed this on my computer really quickly. So for 10,000 observations, which is not at all large by today's standards, inverting a matrix once took upwards of 2 minutes. And then when you embed this in an iterative scheme,
Well, I'm glad we pre-recorded it to avoid technical difficulties.
I can always give the talk live if we need to, I guess.
Please hold one moment. Christina's working on it.
Okay.
such as a maximum likelihood algorithm or an MCMC algorithm, whatever, where you have to invert this matrix over and over again, potentially hundreds or thousands or tens of thousands of times. This is going to take forever. And so we aren't able to analyze really large data sets using a pure Gaussian process very well. So the main focus of the paper is to showcase a lot of different methods for handling, for using Gaussian processes in the context of large data. Now, I come from the spatial background, so everything in this paper is motivated from that spatial background. But this can certainly be applied to whatever application you are looking for in your field of work. So over the last, let's see, 10 years, maybe even a little more than that, 10 to 15 years or so, this has been a very hot topic of statistical research and efforts. And there's been a lot of different methods pop up by lots of different amazing research groups from across the globe. I'm listing a few of these here. So we have, nearest neighbor, predictive processes, fixed rank creating. These have all popped up very recently. And as someone who uses this methodology a lot, I started to ask myself the question of, well, how is it that all of these different methods can pop up and every single one of them can claim to be better than the other in such a short period of time? So I began to sympathize a little bit with Syndrome from The Incredibles, who says, well, if we make everybody special, then nobody is. And so I just started to ask myself questions on, well, which method is best under which scenarios, and how am I able to tell? And so in order to investigate this problem a little bit more clearly, I enlisted the help of all of my co-authors to engage in a friendly case competition among these different methods. So let me set up the background of what the case competition is. So I took a satellite image, a remote sensing satellite image of land surface temperatures from the MODIS satellite. And I just pulled a data set of about size 100,000, which is the one on the left here, figure A. And then I filtered it out using a cloud cover missing data pattern on a different day to obtain the figure in figure B. So what we end up getting is, in figure A is the full data set, and figure B is the test set of, you can see, well, figure B is the training set, and everywhere in gray is a test set of about 50,000 observations that I was going to have each group generate predictions for. On top of that, I also simulated a full data set of about the same size, and then applied the same masking scheme to that simulated data set. So the friendly competition was set up as follows. We have these, both a simulated and a real data set, both of about size 100,000. and a test set size of about 50,000. I passed just the training data set to each group, as I'll go through in a minute. And they coded up their own methodology for it, sent me the code, and I ran the code on all of my university servers. And I calculated all of the results in terms of root mean square error and the different results that we'll see later on. So the novelty of this approach is that each group who had expertise of their specific methodology and were oftentimes the developer of that methodology, implemented the method, but no group actually saw the test set. So they didn't know how they did until after I ran all the results. So there was no way that they could have tried to game the system, if you will, and make their method look a little bit better on the test set because they just didn't have it. Okay. So that was the setup, and I'm going to run through really quickly the different competitors, the different teams that were involved in this friendly case study competition, and give a little background to their method. Now, I will say that in the interest of time, I'm not going to spend very much time giving these methods their due justice, and I strongly recommend you go and read the paper for more details, or even better yet, go read the original paper that the methodologies are based on, which gives even more detail than we were able to provide in this review paper itself. So I'm going to run through these methods really quick and give you an idea of their different strengths and weaknesses and the different setups. So potentially the earliest, there were two that came out in right about 2009, I want to say, maybe it was even 2007. Based on the idea of basis function expansions. Noel Cressy and Andrew Zamit-Manjon and others came up with this idea of fixed rank kriging, where you take your process, your response variable y, and then you just capture the spatial variability in that process using a set of known fixed basis functions. Now they recommended what they call bi-square basis functions, which are nice because they're tapered. So you end up getting a pretty sparse set of basis function expansions. And then by doing this, since you're capturing all of the spatial variability with basis functions, you're able to just model the remainder error using IID random deviates. Now, importantly, the number of basis functions that you use needs to be far smaller than your number of observations. So if you have 10,000, 20,000, whatever observations, you can usually get away with a couple hundred different basis functions to capture the majority of the spatial variability. And that is essentially dimension reduction technique. And so that the overall rank of this matrix is far less than the overall size of your data set, and that speeds up computation by quite a bit. Along the similar lines are what are called Gaussian predictive processes. These use basis function expansions as well. However, the basis functions defined here are not fixed. Rather, they are motivated by the Gaussian process itself. That is, they put down a set of knots at these S star values, per se. And then your basis functions are then the kriging estimators from those different locations to the observations in your data set. So under a mean zero assumption, this would be essentially your basis functions for predicting from this set of knot locations to the set of observation locations. But again, the key, just like fixed rank kriging, is where you allow the number of basis functions, or the number of knot locations in this case, to be far less than your actual number of observations, and that reduces your dimension by quite a bit, allowing you to do much faster computation. Covariance tapering, on the other hand, tries to lean on principles of sparsity. So if you have sparse matrices, calculating the inverse and determinant of sparse matrices can be done quite quickly if you know the sparsity, or if you have sparsity. So what Reinhard Führer and Doug Nitschke and others came up with is they said, well, we're going to take your original correlation function and we're going to introduce that or multiply it by a tapered, by what they call a tapering function. And they prove, and it's quite easy to show, that still results in a positive definite correlation function. But the nice thing about it is with this tapering function, it actually goes to exactly 0 when the distance between two locations is bigger than some cutoff distance. So what this does effectively is give a lot of zeros in your correlation matrix, which allows it to be inverted much quicker and easier. Doug Nishka, who also worked on the covariance tapering approach, realized, hey, maybe we can get some added benefit by combining the two ideas of a basis function approach and a sparse matrix approach. So he introduced what's called lattice Kriging. He and others introduced what's called lattice Kriging, where they do the basis function expansion using a set of fixed and known basis functions. He recommends the Wendland basis functions. He likes those a lot. But then your coefficients here, these theta coefficients that I have right here, we're going to model that using a sparse precision matrix using principles of Markov random fields. And so now you get some dimension reduction, not as much as in fixed rank Kriging or Gaussian processes, but you get some dimension reduction, but you also allow these coefficients to be related to one another. So you're borrowing strength in estimation, but you're doing so in a computationally feasible way by having these coefficients follow some sparse matrix operations. So that's lattice Kriging. Related to it is our models based on stochastic partial differential equations. This is based on work by Finn Lindgren, who's at the University of Edinburgh, and others. So they're saying, okay, well, let's do the basis function approach as well, along with the sparsity. However, leaning on his novel and his novel paper linking stochastic partial differential equations and Markov random fields, he chooses this inverse or this precision matrix to be approximately equal to your original correlation function. So this allows you to choose a popular correlation function, for example, the exponential correlation function, and then you achieve computational benefits by doing basis function expansions, but then you also maintain properties of that correlation function by approximating the prior on your coefficients to match what that exponential correlation function says it should be. So this matches and sort of marries the two approaches of being able to use a correlation function that you like, along with techniques of basis function expansions as well. Matthias Katzwitz at Texas A&M has developed a lot in this arena of dealing with large data sets for Gaussian processes. One of his approaches is to use what he calls multi-resolution approximations. Again, this is a basis function expansion. However, I'm going to use this figure. It's a little bit easier than the notation to show you how he sets up his basis function expansion. So first of all, he starts with the whole domain, say 0 to 1, and this can be generalized to the spatial domain as well. And he has a couple of basis functions that span that entire domain. But then as he defines more and more basis functions, he partitions the domain into smaller and smaller regions. And each basis function that lives within these smaller regions is confined to or tapered to live within that region. So that gives a lot of sparsity in the basis functions. So for example, the coefficient estimates for the basis functions here are only governed by the observations that fall within that partition. Likewise, the only observations that govern the coefficients of these basis functions fall within that same region. What that allows him to do is set up a massively parallelizable estimation algorithm. And so if you have access to supercomputing or even on a small laptop like this, you can parallelize the computations associated with the multi-resolution approximations. So you can have a ton of basis functions. You can even have as much basis functions or more as the number of the number of observations. However, because of the way that they're set up, you can parallelize things and the computation can go very, very quickly. Andy Finley and Avi Dada, they developed a different approach, which they call nearest neighbor, or they've sort of changed that terminology a little bit to include, to be called Vecchia processes, based on a paper by Vecchia, who kind of introduced the idea back in the 80s, maybe. But essentially, the idea is as following. You take your joint distribution of all of your data, which is, this is a computationally nasty thing to look at, and then you factor it into a series of conditionals. However, we can approximate the series of conditional distributions only by looking at, say, the conditional distributions given only those in the nearest neighbors. So anytime you're doing prediction, the principle is, if you're trying to predict at a certain location, you just need to look at the closest observations, not all of the observations. Not all of the observations. You just look at the ones closest to where you're trying to predict. And so this Vecchi is the one that showed that this is a pretty good approximation. And certainly as your neighbor set size grows to be the size of the data, this approximation is equal. So with theirs, they achieve a lot of sparsity because they only look at the nearest neighbors in predicting the observation for observation I. So that gives sparsity in the precision matrix, which makes computation a lot easier to come by. Similar to this idea is local approximate Gaussian processes developed by Bobby Gramercy. He just looks at all of the complete conditional distributions. So he just looks at, say, using sort of Gibbs approximations. He looks at, say, the observation of a single observation given all of the observations near it. And Bobby spends a lot of time trying to understand what is the optimal neighbor set to use, what's the how do we find that optimal neighbor set in order to make this approximation as close as possible. Joe Guinness over at Cornell University advocates for transferring everything into the spectral domain. So he's done a lot of work on spectral analysis of spatial processes using discrete Fourier transforms and fast Fourier transforms, etc. But the main idea is you transform your process via fast Fourier transforms into the spectral domain, and the discrete Fourier transform is essentially a decorrelating transform, so that now things on the spectral domain are essentially independent, and life with independence is much easier computationally to handle. I've done some work on the simple idea of spatial partitioning and clustering. So this is effective ways to chop up your spatial domain into homogeneous regions. And we based our clustering and partitioning based on an approximation to the gradient. So we essentially say if the gradient is large, then we're going to want to separate. If the gradient is large between two observations, we're going to want to separate those into two different regions because they represent two different. They're just sort of different spatial properties in those two different regions. But then once we define the clustering or the partitioning, then we just fit a sort of a clustered within cluster spatial process model that's much computationally easier to fit because the size of the number of observations in any cluster is significantly reduced from the whole. Florian Gerber, along with Reinhard Feurer, they advocate for what they call a gap fill algorithm. This is not a probabilistic model per se, but more of a prediction algorithm, machine learning type algorithm, where they use the nearest neighbor ideas, but so you generate a prediction based on a weighted average of your observations, but these weights, they optimize over the prediction based on some non-stationarity characteristics, etc. So they are using nearest neighbor ideas or Vecchi ideas. However, they do so in an optimal way for non-stationarity and things like that. Raj Gohanayogi at UC Santa Cruz advocates what he calls Bayesian metakriging. This is a pretty unique idea in the among the competitors here, in that he will partition his observations into different sets, say capital K different sets, and then he computes K posteriors in parallel. So we'll just divide the data set into capital K different groups, find a posterior distribution within each group, And then in order to find the overall posterior distribution, he just finds the geometric median of all of those posterior distributions. So this allows efficient computation by taking all the observations, splitting them into groups, doing all the calculations on the different groups separately, and then pulling those results back together. Similar to a feel of sort of my mind just went blank, some missing data algorithms and whatnot. But he, by splitting this data set up into different pieces, calculating each posterior is not computationally difficult based on the size of that data set, and then pulling it together to calculate the geometric median posterior. Okay, so those are all a very quick run through of all of the different competitors and all the different groups that were involved in this. And so again, I advocate for you to go read the paper or read the original papers that talk about these different methodologies. I wasn't able to, in the interest of time, give sufficient details on a lot of these. So let me just give you a quick run through on all of the different, on how everything's shaped up. This is for the simulated data. For those that could allow parallel processing, I put the number of cores used over here, and just to kind of give an idea of how many cores were used there. But the thing that strikes me here is how well every single one of these methods actually do. The original data, the range was about, so the minimum to the maximum was about 30. And then the root mean square error is less than 1. A lot of times the maximum seems to be the fixed rank Kriging here, a value of only 1.31. So every single one of these methods did extremely well in prediction. One of them had to come in last place. In this case, it was a predicted process of 1.43, but on the scale of the range of the data, that's still a very, very small number. So in terms of point prediction, they all did very, very well. In terms of uncertainty quantification, that's where we start to see a little bit of discrepancy between these, right? So with this column here represents a 95% prediction interval coverage rate, or if you'd rather, this is an interval score based on proper scoring rules of knighting. And you can see there's really a difference between these methods based on their uncertainty quantification. Ideally, all of the coverages would be about 95%, and these intervals would be somewhere close to, the interval scores would be somewhere close to 0. So for example, I'm going to highlight gap fill a little bit here. Their coverage was pretty low, but keep in mind that gap fill wasn't really designed to do uncertainty quantification. It was more of a machine learning fast prediction algorithm as opposed to a full statistical model. So, I mean, that's where a lot of the discrepancy came up. Another place where the discrepancy came up is how well they did in predicting locations that are a different distance away. So for short distance predictions, which are down here, all the observations are all of the methodology, are nearly indistinguishable. But then as soon as you start saying, okay, well now let's predict a little bit farther away from where we have data, now you can start to see a little bit of discrepancy. For example, multi-resolution approximations seem to do okay, at least on simulated data. We'll see that's a little bit different for the true data in a second. But you start to see a lot of discrepancy in the continuous rank probability score and root mean square error in terms of long distance predictions. For the real data, again, numbers went up relative to the simulated data, but that's to be expected. Real data is a little bit always messier than anything we can simulate. So, but these numbers are still very small, and there's not a lot of discrepancy. Again, commenting on uncertainty quantification, some of these methods do better than others. Nearest neighbor Gaussian processes seems to do very well across the board. With a low root mean square error coverage, uncertainty quantification is right about on time, and then a crazy fast computation time of only 2 minutes to fit 100,000 different observations and generate 50,000 predictions. So those seem to be doing really well, but everything seems to, I mean, along with stochastic partial differential equation approach, seems to be doing very, very well. Really low root mean square error, nice coverage results as well. A little bit more computation time, but still performs very, very well. Here again is that same figure as before, except on the real data. again, we see the difference in predictions for long versus short range predictions. So when you have observations that are close to the place you're trying to predict, all of these methods do very well. But then as you're trying to predict a little bit farther away, things, there's a discrepancy between the different methods. So conclusion, overall conclusions that I came up with is, everyone really is special. Here I was before I started this project complaining that, how can everyone be the best? And then, I run this case competition study, and I really realized that all these methods are extremely good and can be used, with confidence, and they do very, very well. A small disclaimer on the time comparison. When we ran this study, these methods were at different phases of development, and the different groups had developed different software. For example, Bobby Gramercy had a full R package available that utilized parallel processing and lots of different things, whereas others that were slower only had like skeleton R code because their methods were newer at the time that we ran all these analyses. So I wouldn't put too much stock into the time comparison. Also, I did not restrict the amount of time that groups were allowed to spend on this, and some groups were just, let's just plug it into my function and let it run, and others spent more time trying to nitpick about approximations and basis functions and different things like that. So I didn't limit that. Also, 100,000 observations really is not big by today's standards. One of the problems with doing a review analysis like this is as soon as it is published, it's out of date. And some of these groups have come up with bigger and better methodology. They're handling millions of observations. I think Matthias Katzfuss down at Texas A&M, he's in the tens, maybe he's pushing hundreds of millions at this point with some of his latest methodology. Really impressive stuff. If any of you are interested in seeing the code for running all of this, Finn Lindgren put all of the code from all of the groups up on his GitHub account, along with all of the data sets are there. The test and training data sets are there. And so you're welcome to go if you have a new method that you want to try and you kind of want to benchmark it against what we've done here. You're welcome to just go and grab those data sets and see how well your methodology does. So let me again thank the organizers for letting me come give this presentation. And I hope what I had to share is helpful for you in your own research.
Thanks a lot, Matt. So now we can do questions. The question and answer session, if you have a question, please type it into the chat room and then I'll read the question to Matt and then he can give an answer. So you've probably been following along with these questions on the chat room, but let me maybe rephrase a couple of them and push them to Matt. And if anyone else has any others you'd like me to ask, please type it in. So Louise Ryan asked about a spectral analysis, and she was wondering how a spectral analysis goes in 2 dimensions. She'd only seen it for time series data. Matt, do you want to say a little bit more about the algorithms used to take Fourier transforms into 2 dimensions?
I actually think you're probably more qualified to answer that question than I am. I think the Fourier analysis is the one I'm least familiar with. But I'll just kind of give a brief reaction. So the problem with moving to Fourier analysis in 2-dimensional is the periodic assumption. So what you essentially have to do with the spectral methods is you have to extend your spatial domain beyond where you're doing the data modeling and kind of wrap it in a way that the periodic assumptions and the periodicity that you use with the spectral analysis is makes more sense and can apply to the spatial data. The other thing that the spectral analysis in spatial data has to have are regularly spaced observations. So if you have really irregular observations across the spatial domain, I think it's pretty difficult to use it in that situation. But in our case, we had a grid of observations, so we were able to compare it that way.
Okay, thanks. The next question comes from Rashita, and her question, I'll just read it. is what are the disadvantages of using this method? Will you prefer this process in all cases over local indicators of spatial association? I guess that's LISA. Tools for calculating local levels of spatial autocorrelation indices to understand the clustering of a disease in an investigation area.
I have a hard time answering that question because I'm not too familiar with the local indicators of spatial. I mean, I've used them like a little bit, but I'm not super, super familiar with it. I think I do like the reason I like the methods that we showed here is that all of them, with the exception of gap fill, are fully probabilistic and full statistical models that come along with uncertainty quantification and things like this. So so I like it as opposed to just sort of exploring spatial association tools, which I certainly think have their advantages as well. So in terms of clustering disease and clustering stuff, I don't think these methods can be, I mean, we could probably adapt them a little bit to use them for clustering, but that wasn't the focus of what we tried to do. It was primarily a prediction comparison competition. So I hope that answers your question, Rashida. I hope I answered it okay.
Okay. And then the question I was going to ask, which is very similar to what Louise asked, was how generalizable are the results? So the issues that she raises are the same that I was thinking, or when I read this paper, I usually think. One is that the simulated data and the real data, you only consider one sort of type of spatial process, which is a very smooth process. So I guess the question would be, what if like the spatial correlation was less and there was more like just measurement error? And then another question is dealing with non-stationarity. So if you're not familiar with spatial statistics, non-stationarity means that the spatial correlation is potentially different in different subdomains. So maybe a strong correlation in the north and a weak correlation in the south. And with these really big data sets, usually they're big because they cover a vast spatial domain. And so oftentimes non-stationarity seems more likely than not. So Matt, do you have any conjectures on which methods might work the best in these other cases, or maybe future studies that you'd like to do to investigate this?
Yeah, so that's a very fair criticism. There's so many things you can look at, right? You can look at the range of correlation. You can look at lots of different types of non-stationarity. We considered going down that route when we first got started. However, because there's so many different ways of doing this, that we opted to say, let's try and write this from a practitioner perspective, where stationarity is typically assumed, and so the easy, so the baseline case. One comment we got that I think would be, if I were to redo this study, this is how I would do it moving forward, is have each group simulate their own data sets, because each method has their own strengths and weaknesses. So nearest neighbors, because you're only looking at local regions, has the ability to capture non-stationarity a little bit better than, say, Gaussian predictive processes or fixed rank kriging. So if I were to redo this, I think one thing we learned was have a data set that matches each method. So you would simulate a data set from each method and then see how well do the other methods fit data that comes from that specific method. And that way you'll see a lot of variety. You'll see some non-stationarity. You'll see short and long range correlations. You'll see varying degrees of smoothness in the spatial process. And so I think that's something we learned from this is kind of you always know how to set it up better the next time after you do it the first time, but it was good first go at it. So I would, in terms of how generalizable the results are, from what we've seen since this study came out, it seems to resonate with where the research direction has been going. So nearest neighbor and Vecchia processes have received a lot of attention recently in the last 3 years, because they seem to be really robust with respect to the type of spatial process you're modeling. And so I think they're generalizable to some extent, but you have to still limit it.
Okay, and let me ask one more less technical question. So I think this idea of having a competition is really great. I know I just wrote a review paper where I had to code up myself like 10 different methods and it was terrible. And I would have loved to just emailed all the people with their individual papers and had them do that part for me. So I think this is a really neat idea. Do you have any advice for somebody trying to set up a future competition like this, or maybe collaborative effort like this? Is there like guidelines that need to be in place or advice you give the users or the organizers?
No, that's a good question. Luckily, I've been really fortunate that I know all of the authors personally, so that helped a lot in convincing them to do this, and my appreciation goes out to them for being willing to put their method out there on the line and see how well it does. There was in the writing there was a lot of kind of back and forth on like, well, let's tone down your criticism of my method a little bit. So there was a little bit of that, but in terms of advice that I would have, I think if you really do have to be open to a lot of different ideas that might come in and people's opinions on it. So having an open mind to which method might work and trying to get a wide variety of methods as well would be nice, is certainly nice. But I don't know if I have too much good advice other than I was really lucky that I knew a lot of these authors, and so I could ask them personally and convince them. So sorry, I don't have too much advice, but
No worries. All right, well, thanks, Matt, for an excellent presentation. I would clap, but we're all on mute. So I'll just say thanks again and pass it off to Gert for the awards.
Okay, well, thank you very much, Brian, and Matt for the nice session. Of course, it's also my pleasure to welcome all people present here to this session, which, of course, as you all know, was planned to take place at our International Biometric Conference, planned to take place last week in Seoul. Unfortunately, the meeting had to be canceled due to COVID-19, as you all know. But all people involved in the planning of the original meeting, they joined forces and they have been able to set up a very nice virtual program containing various aspects of the original program, and the whole program has been spread over the entire summer. So I very much would like to thank all involved in setting up this virtual program. As was already briefly introduced by Brian, it's become a tradition to have a JABES showcase session at each IBC, during which the two best papers in JABES by an IBS member, one for each of the two preceding years, are presented. As a society, we very much welcome the selection of those papers, as we believe this is the best kind of publicity for the research of our members, as also Brian was indicating. So I really would like to take the opportunity to thank Brian for making the selection. It's very much appreciated, and thank you also for agreeing to offer the showcase session, or at least this part of the showcase session, at our virtual program, and there's another one coming up later this week. The paper that we have just been listening to was selected as the best paper for 2019. Congratulations to all authors, and thank you, Matthew, for presenting the paper. I'm very happy to confer upon you and your co-authors the award of Best Paper published in JABES in 2019 by an IBS member. Usually, in normal circumstances, I would now give you a certificate. Of course, this is no longer possible now, but the certificate will definitely be mailed to you later on. Congratulations again, and I would like to conclude by thanking you all for attending and by inviting you to participate in future online meetings or sessions later this summer. And as mentioned before, there is a next one on Thursday, which is the second JABES showcase session. And by this concluding note, I'm really happy to hand over to Christina for closing the session. Thank you very much.
Thank you very much.
Congratulations again to Matthew. We hope that everyone had their questions answered. Any questions which were submitted through the Q&A feature, which we were unable to answer during the session, can be responded to after offline. We hope to see you online in the IBC 2020 community. You can also keep up with the conference via the Society's Facebook, Twitter, LinkedIn, those social media accounts. Links to all the platforms can be found on the IBS homepage. As Garrett mentioned, on the 16th, we will be hearing from our second session for the JABES Showcase. Erin Schleip will be giving her presentation. On the 20th of July, we will hear from our third keynote speaker, Diane Cook. So we encourage you to join. And we are excited to announce a statistics and practice session that has been scheduled for the 23rd of July. This will be held in 2 different sessions. However, prior to attending those sessions, you are asked to watch a pre-recorded lecture. This lecture can be found on the IBC 2020 website under Schedule Events and Showcases. You will be instructed to download and install the relevant R packages and then participate in a hands-on practical workshop where Sam and Garth will offer practical advice on using the tools. We encourage you to visit ibc2020.org, check out the latest schedule. We will be posting the recordings of all sessions, so you will also be able to find those there in the community. Make sure you double check the time zones listed for each session. And so thanks again for joining us today. You may now disconnect from the session. Thank you.
Thank you, everybody, for coming.
Thanks, everyone.
Thank you,
Congrats,
Matthew.
Matt.
Thanks, Brian. Great job, Matthew. That went really well.
Yeah, thanks for setting it up.
Yeah.
Appreciate it.
Thank you. Thank you very much. And
All
congratulations again.
Thank you. It was an honor. Thank you so much. So,
All right, guys.
anything else you need from me, or we're good?
Nope, I think we're good to go.
Okay.
I'm gonna
Awesome.
cloose out the session now. Thank you, guys.
All right. Great
Thank
seeing
you.
Bye,
Take care.
everyone.
Bye.
Thank you.